Okay, this video is the last part, which is part 4 of lesson 8 on synchronous generators, and we are going to talk about the voltage control of synchronous generators, especially when these generators are working alone. Okay, in this subsection, as we are going to look at the control of the voltage. We are talking here the output voltage of the generator, and in order for us to be able to control it, we need to know the behavior of this synchronous generator when it has load applied to it, and the behavior varies greatly under the load, depending on the power factor of the load, and secondly whether the generator is working alone or in parallel with other synchronous generators. In real practice, mostly this generator will work together with other generators as part of large power system. However, the scope of our discussion is limited to the synchronous generators working alone. And for this subsection, unless otherwise stated, the speed of the generator is assumed constant. Now we are going to see what are the effects when the load changes. An increase in the load means that an increase has been happening in the real power and or the reactive power drawn from the generator. Yeah? So this is what is meant by the increase in the load. And since when the load is changed, the field circuit is not affected. It only affects the armature circuit. Yeah? And because the field circuit is not affected, the field current is also constant, and therefore the flux will be constant too. Yeah? And since the speed is assumed as constant, as stated in the previous slide, then the magnitude of the internal generated voltage EA will also be constant, yeah? As EA is equals to K flux omega. Yeah? EA is equal to K pi omega. Yeah? Omega is constant, flux is constant, K is a constant, and therefore EA is also constant. Now, assuming the same power factor of the load, change in load will change in the magnitude of the armature current IA, i.e. if the load is increased, then the magnitude of IA will also be increased, and vice versa. If the load is decreased, then the magnitude of IA is also decreased. Okay. However, the angle will be the same for a constant power factor. Thus, the armature reaction voltage JXSIA will be larger for the increased load. Since the magnitude of the internal generated voltage is constant, i.e. EA equals to V pi plus JXIA, the armature reaction voltage JXSIA vector will move parallel to its initial position, as we will see on the following slide. Okay, now we will see what will be the effect when the load is increased. Yeah? So, if the load is increased, we learned that IA will also be increased. Yeah? And if you see the prime, all the notations with the primes, with the prime is representing the condition after the load is increased. Yeah? So initially what you have was this IA, yeah? And then you can see that this is the initial phase voltage, and this is the initial JXSIA, and this is the initial EA. Yeah? or internal generated voltage. Now IA is increased. So instead of this IA, we have this IA prime. Yeah? And as you can see, the length of the vector of IA prime is longer than IA, which means that the new IA is larger than the previous IA, and this is because the load has been increased. Now from there we look at this EA. We learn that EA is constant and why EA is constant, because EA is equal to K flux omega, and flux and omega are not affected by the load. Yeah? The flux is induced by the field current, and field current is on this field circuits, which is not linked to the load. Okay, and the speed of the generator has been assumed to be constant, and therefore EA, which is equal to K flux omega, is also constant, or K pi omega. Okay, so EA is constant. It means that the length, the length of the new EA will be exactly the same as the length of the previous EA vector. Okay, it means that it can only pivot around this origin, so it can follow this arc. It's either going in this direction or that direction, but it will always follow this arc, meaning that the length of EA is constant no matter which direction is going, either upwards or downwards. Okay, right. And then because IA has been increased, it means that J excess IA will also be increased. Yeah? Okay, so this is the original J excess IA. So the new one will be longer, because J excess IA is increased. Yeah? So it means that it cannot go downwards, because if it go downwards, then this because the EA is constant, you can see that the length of J excess IA will be shorter. So it means that it has to be moved in parallel to the left, towards the left rather than to the right. Okay, and we get that this is the new J excess IA, which is longer, and still the end of it is meeting the arc, which is the limit of the length of EA, and therefore this is the new EA that we get. It's number 4 here. This is the new EA that we get, and you can see that it means that V pi is now represented by this V pi prime, which is the phase voltage, which is shorter than the original V pi. So it means that if the load is increased, then the phase voltage will be lower. Okay, that's number 5, the new V pi. Okay, so that was the new V pi. The same diagram has been redrawn here as diagram A, and that was actually specifically for lagging power factor. That's for lagging power factor, and you can see it from the angle of IA, which is negative. Okay, now what will happen if the power factor is unity, or if it is leading? B is for a power factor is unity. You can see the angle of IA is 0, and C is when the power factor is leading, and you can see that from the angle of IA is positive. And you can see for the first one, we already saw that the new V pi will be smaller than the original V pi, and for unity power factor, the V pi is also, if you see, is also smaller, yeah, but only slightly smaller. But when it comes to the leading power factor, you can see it's the other way around. The new phase voltage is actually larger than the original one. Yeah? So in order for us to be able to determine what will happen to the phase voltage, whether it's increase or decrease, when the load is increased, we need to know the power factor, and that's why in the previous slide that we already stated that the behavior of the synchronous generator depends on some factors, including the power factor of the load. Okay, and this slide summarizes all the effects of the change, yeah, especially the increase in the load for the different power factors, be it lagging, unity, or leading. Yeah? And you can see, you can read it yourself on in the table here. Okay, so the effects of the change in the load is in the change in the phase voltage, and this lead to the change, yeah, the effects on the voltage regulation as well, yeah? Because the voltage regulation is given by the no load voltage minus full load voltage divided by the full load voltage times 100%. Okay, and these voltages are closely linked to the phase voltage of the generator, right? So as the effect that on the voltage regulation, when the power factor is lagging, a fairly large positive voltage regulation that you will have, yeah? And then if the power factor is unity, then you will get a small positive voltage regulation. And if the power factor is leading, then we will get a negative voltage regulation. I'll get one example. For the leading one, you got negative, yeah? Because now the no load voltage is actually smaller, yeah, than the full load voltage. Okay, and if you look at the previous slide, that you will see that the V pi prime is larger than the V pi. This happens for the leading power factor. Yeah. Okay, and the full load voltage is actually referring to this, yeah? Because when you increase the load, then until its maximum, then you get the full load voltage, and this will be linked to the no load voltage, yeah? Okay, and because the VFL is larger than the VNL, then you get a negative voltage regulation, yeah? Okay, and then similarly you can derive this VR by looking at the relation between the V pi prime and V pi for the other two power factors, which are the lagging and the unity power factors. Okay, and then finally this table summarizes the effects both on the output voltages and also on the voltage regulation for the different power factors. Okay, so we have seen that when the load changes, the output voltage of the generator also changes. However, in many applications, we want to be able to control the terminal voltage so that it's constant regardless of the load being applied to the generator. Yeah? So how can we achieve this? How can we control the terminal voltage so that we have a fixed one, a constant one? and not affected by the changes in the load. Okay, since the armature reactance cannot be controlled, an obvious approach to adjust the terminal voltage is by controlling the internal generated voltage. Okay. Yeah, so if you look at the equivalent circuit diagram here, yeah, to allow us to control this, we can either change the voltage here, but as it's been mentioned, it's not controllable. So the only possible way is by changing this EA, or internal generated voltage. And how do we achieve that? Yeah, assuming again that the speed of the generator is constant. Okay, the answer is here. This may be done by changing the flux in the machine while varying the value of field resistance RF. Yeah? So again, we can adjust the output voltage V pi by adjusting EA. And how do we adjust EA? By controlling the field current IF. Yeah? And how do we control IF? Is by adjusting the value of this RF, or the field resistance. Okay? So if we decrease the field resistance RF, then the field current IF will be increased. Yeah? Okay, when RF is decreased, it's also, you can see also from the flow chart here, when the RF is increased, the field current is increased. Yeah? Sorry, when the RF is decreased, the field current is increased. Yeah? And then the increase in the field current increases the flux in the machine. Yeah? So the flux which is induced by the field current will be increased as well. And as the flux is increased, EA will also be increased. Yeah? Because EA, again, you should have remembered this by now. EA equals to K pi omega, and again when the pi is increased, EA will also be increased. Yeah? And then the increase in the internal generated voltage will also increase the terminal voltage of the generator. Yeah? Because V pi is equal to EA minus JXS IA, and minus IA RA. Okay, and then the terminal voltage can be equal to V pi or square root of 3 times V pi, depending on the connection. Yeah? The three-phase connection. Yeah. Okay, and yeah, Vt equals to V pi for the delta connection. Okay, so from this, that we can see that we can control the terminal voltage or the output voltage by adjusting the field resistance. Yeah? And how can we decrease Vt? Is the other way, or the other way around. Then it means that if we want to decrease Vt, we need to increase the field resistance. Yeah? To answer this question here, okay. Right. So this has answered the question how we can maintain a terminal voltage. Yeah? So if the terminal voltage has changed, then we need to adjust the value of RF to enable us to maintain a constant terminal voltage, which is the output voltage of the generator. Thank you.